Welcome again. So basically going through the introductory slides here, and so today's lecture is going to be on distribution, safety and protection. So this will include two aspects. One is the grounding, system grounding, and the second one is going to be protection, where we will look at distribution system typically has overcurrent protection, so we'll talk about that. Different type of devices, relays, breakers and all those things. So first of all, let us look at grounding. Why do we need to ground? That's the main question. So there are multiple reasons for doing it. So I'll go through the discussion here. Grounding is a mechanism to protect distribution equipment and people. So both equipment as well as people have to be protected under normal operating conditions, abnormal conditions, and hazardous conditions such as shock. So under all possible conditions, we have to provide safety. And it is necessary to assure correct operation of electrical devices. If you don't have proper grounding, the equipment will have malfunctions and they won't operate properly. To assure safety during normal or fault condition, to stabilize voltages during transient conditions, and to dissipate energy associated with lightning strokes. So if you don't have proper grounding and the lightning hits the system, it is going to damage the equipment because the lightning has to be able to go to the ground. Now, good system grounding provides the path for normal load and fault currents while maintaining load and controls temporary over voltages. Good equipment grounding ensures safety, personal safety. So what are the approaches for grounding, how we do it? Now in USA there is a general practice that is followed. I think India may have similar or practices, I'm assuming. But Dr. Sharma can tell us a little bit more about that if there is a need to talk about it. So in US, the distribution systems are typically 4-wire systems. So you have 3 phases and 1 neutral. So that's the 4-wire, we call it 4-wire system. If you don't have a neutral, then it becomes a 3-wire system. And then as far as the operating conditions are concerned, you can operate as a 4-wire system or 3-wire system or 3-wire with ungrounded system, which is not recommended, or 3-wire ungrounded delta connected system. Delta does not have a neutral, so you cannot even ground it. But in those cases, typically they would have a tertiary transformer and they'll have some grounding for delta connection. So let's look at some of the common approaches and why one is better than the other. So in this one, what you see is there are 2 possible operating systems. So on the left here, what you see is this right here is on the left is a 4-wire system, and this is has multi-ground. We can notice that you have the 3 phases, and then the neutral is running along with the 4 wires, and the neutral is grounded at the substation as well as at many positions along the way. So this is along the feeder, which is overhead poles, so they will be grounded at different locations. Now even if you have a underground system, that it will be grounded at multiple locations, the neutral wire. And then you see here, this is where one of the phases has the tap with a fuse, and this is what we call as this is the main feeder, and this tap here from the one of the phases is a single phase tap. There is no connection here, it's just wire. Neutral is separated from this wire, so don't get confused here. So this is a single phase tap, and then from this single phase, this is called a lateral, and then we have another fuse here, and then this is the distribution transformer that is connected here. Now this distribution transformer, I think it looks like No, this is okay. It's okay. This is connected to the neutral here. So phase and neutral. And the neutral is grounded right here. And then this is a small transformer. It's kind of mounted on the pole, maybe about 2 feet in diameter. Very small transformer. This serves about 10 to 25 kVA, so for 4 to 8 customers or something like that. And this is where you see that the secondary is split into two parts. It is 240 volts, but half of it is 120, other half is 120. And the midpoint is tapped and connected to ground. So this is a very important thing because the ground has to be common throughout the system. You cannot have one part grounded one place and another part another place. It's a continuous ground that runs all over the place. So this is you are grounding at different locations, and then neutral, of course, is the one that gets connected to ground at multiple locations. Now this is a recommended practice for US system 4-wire with multi-grounded neutral system, and this one is a 3-wire system. Now in 3-wire system you don't have a grounding available anywhere because the neutral is at the substation, so you ground the neutral, but you don't have any other options to ground. So this one has a lot of problem because in this case you have to serve the supply to the individual customers with two phases. Here we have one phase and neutral, but here you have to run two phases. So this is both from safety point of view as well as from other, it's more expensive because now you have to have both sides of the transformers alive. So you have to put bushings and you have to put extra fuses and everything else. So this is a more expensive option. The secondary side still looks the same because you can ground it locally here. But as far as the rest of the system is concerned, it's different. So this is actually much better approach with 4-wire system for safety purposes. So to summarize, the 4-wire systems are superior to the 3-wire systems for serving single-phase loads and are predominant in North America. So that's what the utilities do. And it's also cheaper to build. And so what happens is that it also allows the ground current the fault current to go into the ground. So that also creates safety. Now, as far as the grounds are concerned, it is important because it also impacts the transmission line models. I'm sure you have studied transmission line models. Or how many of you are familiar with Carson's equations to compute the resistance and inductance of a line? No? You don't teach those things, I guess? Okay. RLC calculation.
For transpose lines and all, lines and all, but I remember the name exactly.
Okay. So anyway, the thing is that the resistance and the inductance and capacitance of the line, it depends on the soil conditions, because what happens is that the current is flowing on the line, and then there will be some impact, there will be some current flowing in the ground. So I'm sure EM theory, we talk about the image approach to compute the capacitance and inductance. So those are some of the issues that are important. So the grounding actually helps because what basically it does is that the neutral does not have much voltage because the current goes into the ground. So that allows you to calculate the line parameters more accurately. If you don't have that thing, then you have to make more approximation in terms of calculation and other things. So that's one aspect, and of course the frequency and the soil resistivity, they also have an impact on I think this is effect on line. This is there is an error here, small error I found. It should be just, this should be not on line. This should be just line parameters, effect on line parameters, and that's it. I think this is more like a calculational aspect. Now, also, the ground that you have, the neutral shifts during ground fault, because neutral is connected to the ground. So when a fault takes place, a single line to ground fault, the other two phases will have a shift in their voltage. So in ungrounded systems, the line to ground voltage on unfaulted phases increases to the line to line voltage, which is 1.73 per unit. Okay, and then it depends on if the system is with perfectly ground neutral, there is no shift in the neutral voltage. Because, but there is no perfect ground. It's very difficult to have achieve 100% perfect ground. So typically in system with multi-ground neutral, the voltage can rise up to 1.3 per unit. So that's also an important aspect, because it prevents over voltage from happening in the unfaulted phase. Okay, so this phenomenon, how do you find what is good grounding? So we have some rules for that. And then we define two quantities. One is called the coefficient of grounding, and the other one is earth fault factor. So these are the two things that we're going to define. Coefficient of grounding and earth fault effect, these two things. Now what are they? They're basically, the coefficient of grounding is VLN prime divided by VLL. Now VLL is the rated voltage, okay? So COG is the ratio of the highest line to ground power frequency voltage of a sound phase at a selected location during the fault to ground. This is a single line to ground fault at one phase, and we look at the other two phases and we measure the highest voltage between the two of them, affecting one or more phases to the line-to-line power frequency voltage, which would be obtained at that location with the fault removed. So it's a normal voltage. So this is called the coefficient of grounding. And then the earth fault factor is defined as the ratio of the highest line-to-ground power frequency voltage on a sound phase at the selected location due to line-to-ground fault. Line to ground fault to the phase to ground power frequency voltage. This is the difference is that this is line to neutral voltage, and the previous one was line to line voltage. So they are kind of like, if you go back and look at the difference, this is the ratio. Oh, I think I made a mistake here. This should be, oh no, this is okay. So this is the ratio with respect to VLN, and this is VLL, and the next one is VLN divided by VLN. So VLN prime is the same, numerator is the same, the ratio of the highest line to ground power frequency voltage to a sound phase at a selected location due to a line to ground fault to the, this is, so basically the numerator is the same, denominator is different. So this is the unfaulted phase from one or more phases to ground, and VLL and VLN are the nominal line to line and line to neutral voltages. The system is considered effectively grounded because the normal relationship of VLN and VLL, in this case when the fault takes place, it does not, there are some errors will happen because you have ground effect is there and all those kind of things. The system is unbalanced in those situations anyway. So what is important is the system is considered effectively grounded if COG is less than or equal to 80%, and this will result in, so if COG is less than or equal to 80%, and then this results in EFF equal to 130% or less. Now that's because we are dividing by a smaller quantity here, so it will be larger, EFF will be larger. So if these numbers are not, if this number is higher, then we have to worry about it because it means that your grounding is not good. Okay. And how do we, sometimes instead of just direct ground, a reactance is used for grounding or a resistance. Typically reactance is more popular. The reason is that if you look at the previous slide, one of the previous slides here, right here, if I put right here, if you put a reactance in the ground, right here, if you put a reactance, then if your fault takes place here, SLG, single line to ground fault, then you see that this impedance is going to come in the circuit and it's going to reduce the fault current. So to control the fault current on the distribution system, sometimes the utilities will install a reactor here, which is a common practice because sometimes the fault currents are too high and they want to restrict the current to be for ground faults, so they will put a reactor. Now this, if you pick too big a reactor, that also creates a problem because that will effectively reduce the COG, and you don't want to do that. So it will reduce the fault current, but it reduces the effectiveness of grounding, which results in higher voltages on the unfaulted phases. Okay? So therefore, selection of reactor for neutral grounding must be carefully evaluated by considering the trade-off between the decrease in fault current and increase in voltage on the unfaulted phases. Okay, so that's something important. Now, I'm not going to talk too many details about this grounding situation, but if you are interested, you can, there are multiple standards that are available that discuss more details on groundings, and they are listed in this particular slide. As far as the substation safety is concerned, there are two issues that are important because when you are in a substation, unbalance in three phases of the distribution system under normal operation results in flow of some current from the ground to the substation transformer neutral. So if you are looking at a neutral that is connected to the ground, and then if you are inside a substation, some current is flowing in the neutral because things are not completely balanced. And if there is a fault that is happening, then the fault is actually going to be traveling through the ground. And so you have to be very careful about that. So it can create, because depending on the resistivity of the ground, you can have a voltage that will appear on the ground surface, and that could cause issues in terms of safety. So let's say, for example, if the fault is flowing from the neutral to the ground, it's a single line to ground fault, there is some potential that will be created in the ground. Typically we count 2 feet, a step of a person. So if you are walking, you're standing still, it's no problem. But as soon as you put your step forward, then you are creating a potential difference between the 2 points, and the current can flow through your legs. The path will be just through your legs. So this is called the step potential. And then this one is called the touch potential. So if somehow a person comes in contact with a live neutral conductor, because neutral typically are not insulated, and somebody can touch the neutral during fault conditions. In that case, if you happen to touch something which is in the substation, and the fault happens at the same time, that what you are doing is you are creating a parallel path to the fault current which is flowing here, which is the neutral conductor connected to the ground, and then touching that neutral conductor will create a current flow through your body. So through your hand, it will go through the rest of your body. And these two conditions are very dangerous condition. So to prevent something like this, what they do is they put a mat, grounding mat in the substation. And they are such that it's a very complicated process to design. So it will protect individuals working in the substation against these two situations, like the step potential and touch potential. So again, this is a very top level overview. I'm not going through any kind of calculations, details and everything. This is just to kind of give you a brief overview. Now, if you are interested, of course, there are a lot of textbooks available, and also the IEEE standards talk a lot about that. Now, talking about National Electric Safety Code. Now, this is a code that is being designed. It is applicable in US. I'm not sure around the world who else is using it, but this is primarily designed for distribution systems. Okay, and has been adopted by most of the states in the US, and it has been in practice for over 90 years. So this is the single most important document for safeguarding of persons from hazards arising from the installation, operation, or maintenance of conductors and equipment in electric supply stations and overhead and underground electric supply and communication lines. So anything that has to do with distribution system, this code is the key thing. And so this one has extensive updates and critical revisions that directly impact the power utility industry. It also includes work rules for construction, maintenance and operation of electric supply and communication lines and equipment, because you know that distribution system also require communication lines for managing the equipment and automation and those kind of things. So this is a kind of like a complete guidance for that. This standard is applicable to the systems and equipment operated by utilities or similar systems and equipment of an industrial establishment or complex under the control of qualified persons. While NESC governs the rules for the system under a utilities authority, safety issues related to customers' premises are governed by the National Electric Code. So there are two different things, National Electric Safety Code and National Electric Code, which is different. Now, National Electric Safety Code applies to the utilities distribution system, whereas National Electric Code is beyond the transformer and goes into the people's homes. So wiring of homes and those kind of things. So that's something to keep in mind. Now this is, again, I'm not giving a whole lot of details. This is, if people are interested, you can search for additional literature and review them. Let's talk about National Electric Code. Now this is something that has been adopted in all 50 states of the US. It addresses safety consideration for the secondary part of the distribution system beyond the distribution transformer. So when I showed you a transformer that's connected to the line, and then you have 120 to 40 volts, which is on the secondary side. So anything that from that point on inside the home, National Electric Code is what is used. So this is something extremely important for people who are architects, who are designing buildings, because architects not only have to design an aesthetic looking building, but they also have to worry about how to put wiring inside the house, and how far, like for example in US we have a rule that inside a house, in any room, the receptacles that you put for plugging devices, there has to be 6 feet is the maximum distance allowed, or minimum distance allowed. You have to have within 6 feet at least one plug available, socket actually, to put the plug in. So that's the requirement. So I think those are some of the issues that are very important, because safety is extremely important. I know, because if the systems are not designed properly, it can cause fires. So This is the benchmark for electrical design, installation, and inspection to protect people and property from electrical hazards. And then, of course, it also talks about grounding, because inside the home also you need to have grounding for safety purposes. So, what kind of things we do? Again, this covers a lot of things. So I'm going to just quickly go to the next slide and show you how the grounding is done in a home, which is continuing from the substation all the way to the home, and how that is done. And then, of course, this particular NEC also talks about grounding of communication systems and anything that has electrical. Yeah? So this is an example of how so this is the distribution transformer right here. On this right here this is the distribution transformer, okay, and this is where this is the home, okay, and this is the where the meter is connected, service entrance. You call it the service entrance because the line comes in and the meter is connected there, and then wires go inside the house. So basically, this is, again, I'm talking about the system in the United States, but of course you may have a very similar system here. I think NEC is pretty much used across the world, as far as I understand. So, but there would be similar code for India, I'm sure. So you have the transformer is grounded here, and it is also because this pole could be about 150 to 150 feet behind the house, and the wire comes in, and then you put another ground here, okay, and then we have color coding here. Red is hot, black is hot. There are two live wires, and the neutral is the white wire. So if you check house inside US, you would open the thing, you'll find three wires, black, red, and white. White is the neutral. And the neutral is grounded at the substation, at the service entrance here. And then this ground actually, it is wire is connected. There is no more grounding inside the house. You just run the same wire that goes into the house, and that is connected to all the devices. So every device that you have will have three plugs in it. So you have to provide grounding. So the ground wire is running inside the house, and you connect your devices to that ground. Okay. Now this is how the plug looks in, the socket looks in US, very similar to three-wire socket that we have in India. You have the same kind of thing. So in this one, what you see is the neutral is on the left-hand side, which is the bigger one for some reason. The ground is at the bottom, and the hot is right here. And then this actually, the wire inside the house has to have a certain rule, which is that the minimum size should be 14 AWG copper. This is the size, AWG is the size of the wire, and it is actually the smaller the number is, bigger the size is for some reason. So 14 AWG copper, or if you want to use aluminum, that you have to use a bigger size wire. And then this is for 15 amp circuits, and if you have a 20 ampere circuit, then you have to use bigger wires. Now here is an example of a situation where you have the wires going in. This is the neutral is grounded here, and this is the load, and the ground and the neutral are switched here. Okay, so as far as the load is concerned, it will still work because you have power coming from here, and it's going to, instead of going to the neutral, it's going to the ground. Okay, so as far as iron is concerned, it's not a problem. But you typically connect the ground wire to the equipment like an iron. So if you, instead of ground, if you connect the neutral, then what happens is that if you touch the iron, you are actually creating a parallel circuit from the neutral to the ground. So you will get a shock. So it's very important that sometimes when you're working on, I've seen many times when you go to somebody's house and you ironing something and suddenly you happen to touch the iron and you get a shock, and what's going on there? That's basically the neutral and ground are interchanged. They get the socket is wired incorrectly. So that's something to keep in mind. So next time you go to somebody's house and get a shock, you tell them to get the wiring fixed, because that's the problem. Okay? So moving along, improper grounding in secondary system can cause safety issues, including fire and failure of equipment at homes, because if fault takes place and there is sometimes lightning happens, and that could cause a problem too. And then if you connections are not made properly, it can cause arcing, and that can cause fire. So that's something to keep in mind. Okay, so open neutral of secondary system causes the unbalanced current of the two circuits in the house to flow to the ground. If the two circuits have large difference in their loads, the neutral to earth potential can become high due to large current flowing through the ground electrodes, which can have high resistance. So there are some of the issues that are important to look at here. And it can also cause switching on and off. Loads can cause fluctuations of the neutral to earth's voltage, because if you don't have the grounding, then the voltage, because what happens is that if you put the middle point to the ground, and if there is no ground, then the two circuits will have a lot of fluctuations in the voltage, because as soon as if the two circuits are not balanced, then it's going to cause a lot of circulating currents in the system, and that could cause fluctuations and flicker, which is like a power quality problem. Okay, so that's something about grounding. Now we will shift gears and move to protection overview and philosophy, and talk about different equipment that is used for protection. So any question about grounding? Not right now? Okay. All right.
Earthing or grounding?
What is it?
Earthing or grounding?
It's the same thing. It's a different name of the same thing. Yeah. With earth and ground are the same thing, so just different name. I think in India they probably call it earthing. In US we call it grounding. So, but it's exactly the same thing. So as far as protection is concerned, it's very complex and difficult topics, but it is very important, because the primary philosophy of protection is to preserve sensitivity, selectivity, and minimum time of operation and reliability. The key thing is that when a fault takes place, you want to detect it and operate something to protect the rest of the equipment. Because if you don't do something, then you get a fire and all kind of equipment can damage and things like that. So typically protection philosophy covers, local protection covers about 2 to 3 buses. It's very difficult to provide protection which will cover everything. So usually protection is designed to cover a small part of the system. And like for example, large failures of the system and those kind of things, there are different approaches for taking care of that. The protection typically is limited to a small area. So there are many factors that have to be considered, such as it has to be a cost-effective approach, because when you're trying to protect something, if the protection requires you to spend more money than the cost of the equipment itself, then that's not the right way to do it. So you have to, based on what you are trying to protect, you provide protection which is kind of in reasonable in terms of what you're trying to spend to do it. And typically, distribution systems will need protection against overcurrent and overvoltage, which is like a lower voltage will happen when a lightning strikes or some switching actions take place, like you have capacitor switching will cause temporary overvoltage. Lightning typically does that, and I think with integration of distributed resources, you could have some additional issues. So we are going to just talk about very basic approaches for protection. We are not going to talk about we'll talk about what is happening, but not necessarily talk about some of the advanced approaches, because there are too many of them and nothing has been standardized as such. It is just basically all at conceptual stage. So, but there are the standard techniques that have been in existence for more than 100 years. They are still used, so they are seem to work well. So we're going to talk about that. So why do we want to do protection? Because again, it is to protect equipment. And if you design protection properly, then it will minimize the effects of damage when an interruption occurs, and minimizes the duration of service interruption to the customers. So we are trying to, the goal is to isolate as little of the system as possible, and then try to restore whatever else can be restored as quickly as possible. So the primary objective of performing protection studies as part of a comprehensive distribution planning and design studies. So anytime you are operating a distribution system or even want to design a new system, you have to go through a detailed analysis of protection. So protection will require you first of all to compute all the fault currents for different types of faults, and then you decide what type of relays you will need, where you want to put fuses, where you want to put reclosers, where you want to put all other protective devices. So this is again this could be addition or expansion of a distribution system, and it could be based on proper phase spacing between conductors and selection of insulation. Vegetation management, like for example, sometimes the lines are too close to trees, so you have to cut trees because that also impacts protection. So in general, protection can include all these things, and also you are looking for any other contaminations that could cause problems in the system, such as if you are close to an ocean, there could be salt deposits that can fall on the line and that could cause problems. So what are the protective? This is just a title: protection of power carrying devices. How do you do that? What are the devices? So we have lines, feederals, which include feeders and laterals, distribution, substation, transformer, and distribution transformers. Now, substation transformer is the big transformer that's in the substation, which will be anywhere from 10 to 50 MVA, large transformer, whereas distribution transformers are small, they are 5 to 25 kVA. So that's the distinction. So, but the distribution system protection includes protection of everything. There are capacitors in the system, voltage regulators, and segments of the system itself. And in addition to that, we are talking about distributed energy resources. So they have also to be protected, and of course the loads have to be protected. So we have different types of equipment and devices available for protection. And typically, the protective devices are the weak link in the system, because anytime something happens, you want to sacrifice the weakest link to protect something that is more expensive. For example, if you put a fuse is very cheap. So if it burns, it will protect your equipment. Okay, so that's the idea. It is supposed to protect not only from short circuit but also from overloads, because sometimes overloads can also create problem for the equipment. So let's see what kind of devices are there. Now, protective and switching devices, we have single action fuses. There are different types of fuses that are available: expulsion fuses, vacuum fuses, current limiting fuses, distribution fuse cutouts, automatic circuit reclosers. We already talked about that in the previous chapter. Then the sectionalizers, we talked about that also a little bit. Circuit breakers are the key thing. They are typically at the substation. And then we have time overcurrent relays. Now these relays, in the old days, these used to be mechanical relays. Now we have solid state or static relays, and then in addition to that, we have numerical relays, which are like a computer. They are digital relays. There is no moving part in them. It's just everything is static. Other things include load break switch, circuit interrupter, disconnecting switch, sectionalizing switch. So we're going to talk about all these things a little bit, maybe not go into a whole lot of detail, but talk a little bit about what they are. And we'll also look at some examples on how to deploy some of these things. Okay, so single action fuses. Fuses have a circuit opening fusible part that is severed by current passing through it. So basically, when the high current flows, it melts and breaks the circuit. They can be used for sectionalizing feeder segments to create zones. So basically, a fuse has two purposes. One is that it breaks the circuit when a fault takes place. But in normal operation, if you want to disconnect a part of the system, you can actually use the fuse, remove the fuse. So basically, removing the fuse will disconnect that particular part of the system. So they are like a self-contained device. There is no separate sensing mechanism. They do their own sensing and then operate. There is no sensing as such, but it is a thermal-based situation. They are very inexpensive, but they have to be replaced, because once the fuse operates, it has to be thrown away and a new fuse has to be put in. So the labor cost of changing them is significant from an operational point of view. So if there is a location in the system where you have too many interrupts or faults happening, then you may want to think about putting something different instead of a fuse, because every time the fuse operates, you have to go and replace it. There are different types of fuses available: expulsion fuses, vacuum fuses, and current limiting fuses. Expulsion fuses are the most common kind of fuses. I will show you some pictures of that. So this is kind of like a inside of a fuse, and so what you have is basically this middle part here is the fuse element here. Same thing, the fuse element. This is something which when the large amount of current flows through the fuse, that part becomes hot and it melts. And so this is basically an inside of the fuse. It looks like that. And when the fuse operates, It's going to create an arc and a lot of heat, but they are designed so that whatever arcing and heat happens has contained inside the chamber. So that's how they work. Okay, so we have for expulsion fuses, which are the most common kind. They come in different designations, and typically their characteristics are shown here, which is x-axis is the current and y-axis is the time it takes to operate. And so higher the current is, it's going to melt the fuse faster because I square R. More heat, so faster melting. And they have different, typically they will carry 100% of their rated current continuously without melting. But anytime the current exceeds, then of course they will melt. And they are operating characteristic of fuse links are determined. I think there's some sentence doesn't look right. Operating characteristics of fuse links are, I think it should be, are distinguished by the speed of operation defined by the speed ratio. Okay, and the speed ratio of a fuse link of 100 amp and below is the ratio of the current that melts the fuse link in 0.1 second to the current that melts the fuse in 300 seconds. So you take the ratio of the time and then you divide them, and that tells you this is called the speed ratio. And a fuse link that of rated greater than 100 amps is defined as the ratio of the current that melts the fuse link in 0.1 and 600 seconds. So this is a distinction. And thing to keep in mind is that there are different types of fuses and they will have different speed ratio. For example, in the next slide we see again 4 different graphs, and they are called the K-link, which is the right here in the middle. It is the fast type with a speed ratio of 6 to 8.1. And these are commonly used in urban systems. N-link, which is the one right here, this is the N, and this has a speed ratio of 6 to 11. The T-link are the slow type, which are right here, and these have a speed ratio of 10 to 13, and these are suited for suburban systems. Okay, and then S-links, which are the last one here, these are very slow with speed ratio. Okay, it's a ratio, not ration. Ratio of 15 to 20. So basically, depending on different applications, one can choose the fuse that you're looking for. And the key thing is that these fuses have to be coordinated with other devices in the system. Have you had any protection background? Anybody? Like overcurrent relays, anything like that? So anyway, we'll talk about some of those things. So vacuum fuses includes a fusible element within a vacuum medium. So the previous fuses that we talked about, the expansion fuses, don't have any, they're just inside a tube and that's about it. But there are some vacuum fuses which will be inside a vacuum. Internal features of vacuum fuses include arc runners, shield and ceramic insulation. Multiple cycles may be necessary for low fault currents to butt back the fusible element. Vacuum fuses can be used indoors and under all oil environments. These are more expensive, so typically they are not used as much. Then there are current limiting fuses. These are non-expulsion fuses. These are limit energy to the protective device, reducing the risk of catastrophic failure to the protective devices. So typically what happens is that the fault takes place, initially you get a very high current. So current limiting fuses will not let the peak of the current reach. They operate very fast, very quickly. So as the name implies, they will limit the current from going to a high value. So basic types of current limiting fuses include backup or partial range fuse, general purpose current limiting fuse. Don't worry about all these things because they're kind of like a specialized topic, and they are not used very commonly, only in very exceptional situations. So the main type of fuses that you will find are the expulsion fuses. And of course, this gives a little bit more detail on current limiting fuses. So talks about some specific applications of them, and I'll just skip that and go to the next slide. Okay, this is a typical expulsion fuse, and what we call is there is something called fuse and fuse link and fuse cutout. Fuse cutout is the assembly of the whole thing, and fuse link is just the link itself. So here in this picture, what you see is that this is the fuse link right here. Okay, and then this is a hook. You can take a stick, a hook, and pull it down, so fuse will come down. So disconnect the circuit. And when the fuse blows due to a fault, the high current flows through it. So this is actually the circuit is this is an insulator here. The circuit is connected through the fuse, and when the fuse blows, then it will automatically drop down. The reason why it happens is because this is a visual indication for the linemen when they physically going to there's an outage in the system and they want to physically walk around and drive to see which fuse has blown. So they can look at the pole, and if this fuse is fallen down by itself, which means that this fuse is operated as a blown. So they will have to replace that. Now this is these are two pictures of reclosers, and they are made by two different companies. And I said the recloser is a multifunction protective device with fault sensing and fault clearing capabilities. And these are self-contained and intelligent devices which have built-in sensing and decision-making capability. And of course, the current crop of reclosers, they have microprocessors locally located there. They have intelligence. They can do calculations, and then also they have a communication, so their settings can be remotely changed and so on and so forth. And these two pictures that you see here are, the top one is this one is from it's a Nova NXT is the name of that, and Eaton is the company that makes it. So this is the name of the company. And then this one is called SNC Interrupter Pulse Recloser, and this is made by SNC. So they have different kind of designs, and they are typically mounted, pole mounted on top of a pole. So the pole has to be pretty strong because they have to build special poles to mount them on top of them. Now, as far as the reclosers are concerned, they have advanced microprocessor protective relays are also commonly used. these are also used at the point of coupling with the microgrids in some application, because the microgrid has to be connected to the grid as well as disconnected, so reclosers can be used in those locations. And as I already talked about reclosers in the previous discussion, so this shows the recloser characteristics. So this one has, this is again like a fuse. We have current on the x-axis and we have time on the y-axis, and this is what we call as the fast characteristics, and B and C are the slow characteristics. So the recloser will have a relay that is inside of it with fast as well as slow characteristics. So typically utility, when they want to deploy a recloser, they will choose the fast one is needed, and then you also will use either B or C, one of the two characteristics. And these are something, the reason why we need to have fast characteristics is because the idea is to distinguish temporary faults from permanent faults. That's the whole idea, because you do not want, if you have a fuse, the fuse does not know if the fault is temporary or permanent, it's going to operate. But reclosers have a feature where they can distinguish between temporary and permanent faults. Okay? So they are designed to trip and reclose a preset number of times to clear temporary faults or isolate temporary or permanent faults. So they basically open, reclosers automatically re-energize the line. So they open and then they will close again, and just to test if the fault is still there. If the fault is still there, they will open again and close again. So there are multiple times they'll open and close. The idea is that if you have a recloser here and there is a fuse here and the fault takes place here, and if this fault happens to be temporary, then when the fault takes place, you don't want to right away operate this fuse. So the recloser will open when the fault takes place, and then it will close and open again. And if the fault is temporary, the system returns to normal. But if the fault is permanent, then in that case it will allow the fuse to open to isolate this faulted part of the system. Okay? Now if the fault instead happens to be here, right here, then it will open, close, and then if happens to be permanent, then recloser will open to protect the rest of the system. But if the fault is temporary, after a few reclosing operations, system will come back to normal. So the recloser eventually will either lock out in open position or it will lock out in closed position. If the fault happens to be here, then it will lock out in closed position and it will allow the fuse to blow. If the fault happens to be in this location, fuse does not blow, then it will open and then it will not reclose after that. So, and they have to be coordinated with, there is a circuit breaker here. So the coordination has to happen between recloser, circuit breaker and fuse to provide proper protection, because the key thing is that if the fuse, the fault is here and you want to operate the recloser to avoid the fuse from operating, the recloser should operate faster than the fuse. So you have to choose the recloser characteristics, which is the faster part of the operation, in such a way that it trips before the fuse operates. So time over current characteristics are the key thing here. Everything is based on time inverse over current characteristics. Larger current, smaller time, smaller current, larger time. So this is a typical operation of a recloser. This is normal operation right here. Fault takes place, the current increases to a large value, and then after 2 cycles, the very quickly the recloser will open, and then after a short delay it will close again, and then it will close, but it will it closes, recloses here, and it does not open. It keeps open, closed for a longer time, and then after the first 2 operations, which are the fast operations, the recloser moves to slow operation, because slow operation, that's why it takes longer for it to operate. So, and the reason why you want to do that is because now if the fault is not cleared in the first 2 reclosing operations, that means the likelihood the fault is permanent. So in that case, it allows the fuse to operate. So after 4 cycles, 2 fast and 2 slow operations, then it will lock out, either in open position or in closed position, depending on where the fault is. So this type of operation is called 2A, 2C, 2 on curve A and 2 on curve B. The recloser can be single phase or 3 phase, but typically they are not really used very much in single phase because they are quite expensive, and it is not in general used widely, but now some companies have introduced single phase reclosers that are not that expensive, and they are very attractive option for situations where you have increased number of faults taking place. So these things can be deployed in those locations. They can be hydraulically or electronically controlled. Interrupting media for reclosers can be oil or vacuum, and most of the modern reclosers are electronically controlled. They also have Wi-Fi and remote monitoring capabilities. And of course, they can be oil-filled or vacuum, but because you are concerned about the weight, because they have to be on top of a pole, the oil-based media will make them very heavy. So vacuum is much more attractive. The sectionalizers are circuit interrupting devices which are similar to reclosers, but are less expensive if they don't have fault interrupting capabilities. So recloser has full. It's not as if you compare a recloser to a circuit breaker has a higher interrupting capacity compared to recloser, because recloser is deployed down the line and the fault currents are lower there. At the substation, the fault currents are higher. But sectionalizers may or may not have fault carrying capacity. Sometimes they don't have, so it all depends. And typically they are deployed in combination with reclosers, and it has a counting mechanism. So typically what happens is that the sectionalizer will count how many times the recloser is upstream, sectionalizer is downstream. So it will count how many times the recloser has operated. So if you have 4 operations for the recloser, the sectionalizer should have 1 less, because by the time the recloser is opened 3 times, then the sectionalizer will open. So I'll show you some picture here in the next slide here. So basically what happens here is that fault takes place, and the recloser opens and closes one time, two time, and then it's going to wait for longer, and then recloser will, this is the open duration, then it closes again, and then at this point, before when the recloser is open, the sectionalizer will open at that same time. So it's not interrupting the circuit under fault conditions because the recloser is upstream and is open. So, for example, if I draw a picture here, the recloser is here and the sectionalizer is here, and then there is a fault somewhere down here, okay, and the recloser opens, it closes, it opens, it closes, and then it opens again, so 3 times. And then it's supposed to close one more time, but what happens is that this sectionalizer is counting, and then the 3rd time it opens. In the meantime, before recloser closes, it will open, and then the recloser will close, and the fault, it will not see a fault at that point because the faulted section has been removed. That's right. So that's how the sectionalizer works. So you actually don't need it to have the fault interrupting capacity. It can be a smaller device. So it's a cost-effective way. Instead of putting a fuse, you can use a sectionalizer. Okay?
It is quite similar to isolator but with automatic.
That's correct. Yeah,
Isolator means another device, but this one has counting mechanism. Isolator does not have.
Okay. So sectionalizers can be used between 2 protective devices with operating curves that are close together. And then they can also be used on closing taps where high fault magnitude prevents coordination of fuses with the backup recloser or breaker. They are also ideal at locations where temporary faults could frequently occur because you have a mechanism to isolate the faults when the frequency is where frequency is high. And they are also designed to automatically reset with the mechanism provided in them. So these are kind of specialized devices that are used. They are not used extensively, but in certain applications they are useful. Of course, circuit breakers are the most important part of distribution system protection or any power system protection, but they are used only at the substation because they are very big and they have very high interrupting capacity, so they have to be placed right at the substation because they are not only providing power to because they are kind of like a transformer is there, and then you have multiple the transformer itself has to be protected, and then you have a bus, and from the bus you have multiple feeders coming out, so they all have to be protected. So they are big and bulky, so they have to be only at the substation. There are different types of circuit breakers, oil-based interrupt, because when the circuit is interrupting, it's creating a lot of arc, and that arc has to be extinguished. So to extinguish the arc, we have to have some medium. That medium could be any kind, and typically oil is one option, and then which are old days oil was used very commonly, but now oil is not used as much because they make circuit breakers very heavy, oil-based circuit breakers, and oil has to be replaced periodically because it gets contaminated when circuit breakers operate multiple times. Vacuum is another option. Air blast interruption is another option. SF6 is very commonly used now because it's the good thing about SF6 is that it makes the size of the equipment very small. The circuit breakers, like something that is huge and bulky, can be made very small. The only disadvantage of SF6 is that it has environmentally not safe to use it. It has some consequences. So from environmental point of view, SF6 is not good, but the technical point of view is really good. So there is a debate going on in the power system community that a group of people are looking for alternatives. A lot of research is going on in terms of what else can be used instead of SF6. I think I saw a presentation or by somebody, I think nitrogen, some people are proposing using nitrogen or something like that. I'm not 100% sure, but there's some other kind of gases can be used instead of SF6. So, and of course, circuit breakers have to be, they don't have their own sensing mechanism. You have to have a separate relay to operate them. Like unlike recloser has its own sensing mechanism right next to it, but circuit breaker you have to have a relay. And for example, in a substation, you have a circuit breaker, transformer, circuit breaker, and all the feeders are going out. The relays are actually not placed there. There will be some kind of a small building inside where all the electronics and protective equipment is placed. So there'll be panels where we would have these relays mounted on the panels. And again, you could have reclosing facility as part of the operation of a circuit breaker, because reclosing, keep in mind, recloser and reclosing are two different things. Recloser is a device. Reclosing is an operation. So recloser already has a built-in reclosing operation, but circuit breaker can or may or may not have reclosing operation, depends on the philosophy of the different operators. Okay, and they are typically motor compressed springs for closing opening operation with spring reset within 10 seconds, or you could have compressed air or other gas for two closing opening operations. They could be pneumatic or hydraulic breakers. Okay, the next item in our list is time over current relays. And these are the workhorse of protection, time over current relays. And they have been in classical electromechanical relays, have been in use since the early days of electricity, dating back to 1880s. So they've been used for a long, long time. And they are still used in some areas of the world, but a large part of it has been replaced by digital, initially solid state, now digital relays. And the only thing is that these relays do a good job, but they are dumb because you set them for some values and you don't have flexibility of changing them until and unless you physically go and play with it. So that's the drawback, but as far as their job is concerned, they do a pretty good job. So this is a picture of a relay which is about 50 years old, manufactured in mid-70s by Westinghouse, and that company doesn't exist anymore because they kind of sold off their business and nobody manufactures these relays anymore. At least in the US, I don't know if there's any company that is making these kind of relays. Okay. They have an intelligence built in to detect abnormal conditions and send proper signals to circuit breakers to trip the circuit breaker. And for example, if you have any kind of system, say we have a 115 kV to 12.47 kV three-phase substation transformer with 10 MVA capacity, and then you have to deploy some relays. The relays obviously cannot be directly connected to the power line, so you have to use current transformers to reduce the amount of current to a lower level. And similarly, the voltage transformers are used in the circuit, which in the system where the idea of voltage transformer is to reduce the voltage to an operating voltage which is 120 volts typically. And so if, as an example, if the circuit has a current of 463 amps, then you would use a 500 to 5 CT to reduce the current from main current to a lower current which can be used for relay circuits. Now, time inverse over current relay is the most common used relay, and it has tap settings. There are some kind of like if you look at the picture here, right there at the top, you see some plugs. Okay, these are the plugs where there are holes, and you see that there is a plug in one of them right here. This is this right here. Now that plug is tap setting. So tap setting. So you have 4 to 12 amps. You can, wherever you put the plug, that becomes your tap setting. Now this is with limited capacity or limited selection of tap values, but with the digital relays you can pick anything you want. You can pick 4.1, 1.1, 1.2, 1.3, is almost continuous. So that's the advantage of digital relays, because they have more flexibility in terms of settings. So you have tap setting that ranges from 1 to 12 amps, and the relay would have another thing that is associated with it, which is called the time dial. And I think in India, the different time multiplier is called. Is that right? What do you call time?
Yes.
Yes. Okay, so this time dial is the same as time multiplier.
That was plug setting.
Okay. So basically, what happens is that you choose time dial, which goes from a time multiplier, which goes from 0.5 to 11, and the relay settings that you see here, basically with higher time multiplier, it will become slower. Okay. So this particular graph shows time current characteristics of a CO8 time inverse relay. Now this CO8 and these designations are again a legacy carried over from electromechanical relays, and they are basically a designation for the inverseness. For example, you have highly inverse, extra inverse, those kind of things. So CO8 is it's an inverse characteristic, but it's not extra inverse, it's kind of in between. Now CO5, for example, is a little bit flatter curve. CO11 is extremely inverse. So there are different names that are used to provide these relay characteristics. Now how do we use them? As an example, in the next slide, I will show a case here. So let's assume that we have a fault current of 960 amps, okay, and we are 960 amps, the CT is 300 to 5, and tap setting is 4. So what we do is we take 960 and want to find how much is the relay current. So we multiply 960 by the CT ratio, and that gives you 16. Now, keep in mind that the x-axis of these relays is not the actual amps. It is the multiple of tap setting. Multiple of tap setting is, if you have tap setting, how many times the current is flowing. So it's the multiple of tap setting. So what we have to do is to find the quantity that is on the x-axis here. We have to find what we call as this quantity, which is MTS, which is okay, and that is computed by dividing the current which is flowing in the relay, which is 16, and divide that by tap setting, which is 4. So you get 4. So MTS is 4, and so we will look at 1, 2, 3, 4 right here. Okay, right here is 4, and this is a graph log scale. This one is log scale. This is also log scale. We use log scale to define these characteristics because you have to compress a lot of data in a small space. So we used to log scale. And then if we have MTS of 4, and it's given that the time dial is 5, so we'll use this 4 and then go up to the time dial of this 1, 2, 3, 4, and go up to here, I think, right there. And then calculate the time which is right here, this point right here, which is 1, 2, 1, 2, 3, 4, 0.4 seconds, that's right. Okay, so key thing is fault current, use the CT ratio, convert it to I relay, and then divide I relay by tap setting to get MTS, and then from MTS you know the time dial, and use the graph with that particular time dial or time multiplier, and then go up and then find the time. Now, so this is kind of like a key thing here, that sometimes you may be given the operating time and the MTS, and you say find the time dial. So either combination can be given, and you can calculate those kind of things. So basically, this is a simple application of using the graphs to find the time of operation of a relay, given that this is the setting of it. Okay. So similarly, for a different current, you can do similar calculation. If the current happens to be higher than this, then you can do that. Now, the reason why these graphs are given in terms of multiple of tap setting is because they become universal graphs. For any tap setting, this will work. Otherwise, if you give them in actual currents, then that is applicable only for a specific setting that you have selected. It doesn't work for all the settings. So that's why the graphs in terms of multiple of tap setting will be applicable to any kind of tap setting that you want to select. Okay. And then, of course, these are the characteristics that were actually implemented in mechanical devices. So you can think about how complicated that would have been to design those relays. But now we can do all those things digitally. And this is an example where although all the relays have been converted to digital form, we still continue to use the existing characteristics that were available from mechanical relays, because mindset of the engineers is already based on historical things. They cannot, and of course, since they work, why change when they work? So we want to continue to keep whatever is working. We don't want to change that. Only thing is we change from mechanical to a digital form, but we still keep the same characteristics. And how do we do that? This particular graph, not equation, excuse me, it gives you the time of operation. T is the time. TD is the time dial. MTS is multiple of tap setting that we talked about. K is a constant. Alpha, beta are also constants. And we can actually use these constants, different values of alpha, beta, and K, and emulate different characteristics. So, as an example here, we have the graph given here. These are based on IEEE data, and similar information is available from IEC, which is the European standardizing agency. But these are these are what we call as different relay characteristics based on their characteristic. For example, you notice that in this graph you have extremely inverse, then CO8 is inverse, CO2 is short time inverse, very inverse, moderately inverse. So these are defined as standard characteristics by IEEE, and they mimic whatever was available from the electromechanical relays. And alpha, beta, and K values are specified in this particular table. And based on these numbers, we can obtain these characteristics. Okay, 2 minutes? Achha, okay. So anyway, I think at this point, I will see how much more I have here. Okay, we already have talked about static or solid state relays. They are based on electronics and don't have any moving components, but they have been in use for a while. They emerged in 60s, and they were being used. Of course, initially the reliability was low, but as the electronics matured, the reliability increased. And now we have moved to digital or numerical relays, which are pretty much since 1980s we have been using them, and they are becoming more and more popular across the board. So I think I'll stop right here, and we will continue on from this point in the afternoon, and then I'll also show you some specific examples of coordination between different devices. Okay? We can have some questions at this point if you have any. You can have 1 or 2 questions. Anybody?
So about the time dial setting or the time to operate any inverse means any overcurrent relay, are there some specific values in case of extra or inverse identity relays? Like
Extra values in the sense?
There was the equation, K, beta, all those things. Are there some values for it?
Yeah. So what you're saying is, are there any else beyond these? No, these are the standard values. Because what they are trying to do is they are trying to model the existing relays, which are 5 different relays. I think that if you have any other characteristic beyond 5, then you can do a similar analysis to come up with these numbers. But IEEE standard that from where I got these numbers, they had only these 5. Yeah.
In my house, there is a voltage in neutral wire. In my house, there is a voltage, near about 10 voltage in neutral wire. So the voltage difference between hot line and neutral is near about 230. But if I make the neutral point with grounding, then the total voltage becomes 240.
Okay.
Then the electricity pins are engaged.
No, but you do not want to ground the neutral inside the house.
Is there any method by in the neutral point 0 I can change, without changing my electric bill I can reduce the voltage of neutral point?
I'm going to think about it. Let us talk about it. The grounding picture, or we don't talk about it. Because I am
I'm still trying to figure out what actually it is. We'll talk about it. Okay? Anything else? Yes.
Power system is transitioning towards the renewables. What modifications are being done in the protection schemes that were previously designed for the conventional power systems? And what are the research areas that we can explore for the modification in the power protection schemes?
Yeah. That's a very good point. I was going to talk about that in the afternoon. But
Basically, what happens is that the renewable resources which are controlled by IBR, which is the inverter-based interface, they have a built-in characteristics that when the fault takes place, they automatically increase their impedance, internal impedance. So the fault current reduces. Now your relay is set to operate to detect that fault, but it is reducing the fault because it is increasing the impedance. So the relay doesn't detect it. The fault stays on the line. So that is a very big challenge. I think that is a topic of research. A lot of people are working on it, and we still don't have a very good solution. So, for example, microgrid has the same issues because you have to provide protection. So anytime you have power electronic interface, the normal protection doesn't work very well. So you have to think about other approaches. And that people, it's an open research topic. People are still working on it. Okay. All right. Well, we'll see you again in the afternoon. One more question? Okay.